All right, so on our titration, we were up to the pH at the equivalence point. So we had 0.12 molar HCl that we had in our burette, and we were titrating that with our 0.20 molar NH3 in our Erlenmeyer flask, which contained 35 mils. All right, so far we did the initial, then we did after 20 mils added, and we are now at the equivalence point. So when you want the pH at the equivalence point, any problem that says calculate the pH at the equivalence point, you're going to have the equation mV over C for your acid is equal to mV over C for your base. All right, and so we have to calculate the volume of our acid. So we know the coefficients, HCl, of course, is 1H plus, NH3 can take 1H. And so our equation is NH4 plus in equilibrium with H plus and NH3. The only equation that we can have both H plus and NH3 in is the Ka reaction. There are three reactions you will need to know: the Ka, the Kb, and the Kw. I will always write them in the order of Ka, Kb, Kw. They will be not the reverse reaction. All right, so at the equivalence point, we have the molarity of acid is 0.12. The volume of acid, we don't know. We are adding it until it hits the neutralization point, where moles of acid equal moles of base, as long as they are 1-to-1, which it is, and the coefficients are 1. So we're finding the volume of HCl required now that our coefficient for our H plus is 1. The molarity of the base, 0.20 molar. We had in our volumetric, or in our Erlenmeyer flask, 35 mils. All right, and the coefficient of the NH3, again, those coefficients, that's a 1. It's understood to be a 1 here, understood to be a 1 here. All right, so then we just push the buttons on our calculator, 0.2 times 35 divided by 0.12. The volume is 58.3 mils repeating. All right, so the volume is 58.3 mils repeating. All right, we only need 2 sig figs, so if the question was what volume is required to reach the equivalence point, well, the volume is 58 milliliters. All right, but we know that the equivalence point, you have to have the exact same concentration of acid and base. Sometimes you need to keep all of your sig figs until the end. All right, so we did mV over C just to calculate the volume of HCl at the equivalence point. Now we have to do mV is equal to mV, a completely different equation because this is acid on this side and acid on this side. And then we do mV is equal to mV because this is base on this side. This is base on this side. This is not the titration equation where it is mV over C with acid on one side, mV over C with base on the other side. This is just diluting it because the acid is 0.12 molar. When we added the 58.3 mils repeating, what is the molarity now that the volume is the 58.3 plus the 35, which is a 93.3 repeating? Again, you don't have to keep all the sig figs, but if you get a different concentration for H plus and NH3, that is wrong. The equivalence point is they are exactly the same. So I do not round any numbers. I go to all of the decimals, and then they will be exactly the same if I do it that way. My base is 0.20 molar. The volume is 35. What's the molarity now that the volume is 93.3 repeating? So theoretically, you only have to do this once because it's the equivalence point and they are the same. but we'll do both of them. All right, 0.075. All right, so when you take your 0.2 times your 35 and divide by your 93.3 repeating, you get 0.075. All right, so they are exactly the same, which is the requirement for the equivalence point. All right, so at the equivalence point, initial 0.75 molar, 0.75 molar. Remember, anytime you write a Ka, a Kb, or a Kw, something on the right has to be 0. All right, in this case, neither one of them are 0, so we have to go to the left until one of them is 0. But they are both the same, which is a requirement at the equivalence point. At the equivalence point, they both go to 0. So minus 0.75 minus 0.75. At the equivalence point, you will have 0 and 0. And on the other side, you will have 0.75. So rewrite this down here where I have more room. All right, so you got your NH4 plus. Initially, it is 0. Our H plus, we just calculated 0.075. Our NH3 that we just calculated, 0.075. All right, and that is our Ka reaction. Something on the right has to be 0, the lowest number. At the equivalence point, they are the same number. If it is 1 to 1, it is the same number. All right, and so now you're going to have your new initial, where something on the right is 0, and in this case, again, at the equivalence point, they will both be 0. All right, so now we can go to equilibrium. Now we have something on the right that is 0, or both things on the right. So now we have minus x plus x plus x. That then at equilibrium is 0.075 minus x, x, and x. And so we have x squared over 0.075 minus x is equal to the Ka. Well, Ka was not given. Kb was given. I think we already calculated that. So the Kb for NH3 is 1.8 times 10 to the minus 5. So to find the Ka, you take the Kw and divide by the Kb, because Ka times Kb is equal to Kw. So 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5 gives us a 5.6 times 10 to the minus 10. So if you want to check to see if you have to calculate, if you have to put your x back in and check it, you take your Ca over Ka, and so you have your 0.075 divided by 5.6 times 10 to the minus 10, and that is much greater than 1,000. So you're going to get whatever, 100,000 or whatever, more than 100,000, 100 million. All right, you're going to get a huge number, way more than 1,000. So you do not have to check your value for x. So x1 is your answer. All right, so you can neglect your x. So you take your 5.6 times 10 to the minus 10, multiply that by 0.075, and then take the square root of that number, and you get 6.5 times 10 to the minus 6. All right, and then you have to see what x is over here. X is H plus. So that is the concentration of H plus, and so we can go right to the pH. The negative log of the 6.5 times 10 to the minus 6. And 5.19 is the pH at the equivalence point. All right, so anytime you are doing a titration with a weak base and a strong acid, when you have your equivalence point, these are both 0, what it made was a weak acid. And so the pH at the equivalence point will always be less than 7 for a strong acid and weak base. All right, then it says the half equivalence point. All right, so now we want to calculate the pH at the half equivalence point. All right, well, this one is going to be very simple. We will work this one out in great detail, and then this is the easiest question on the exam. All right, so if your volume at the equivalence point was 58.3 repeating, then the volume at the half equivalence point is exactly half of that. So you take your 58.3 repeating and divide by 2, and you get a 29.16 repeating. All right, so now we have the same equation. We have our NH4 plus equilibrium, H plus NH3. And so we have to do MV is equal to MV for the H plus. We have to do MV is equal to MV for the NH3. All right, so the molarity of HCl, 0.12. The volume at the half equivalence point is half of what we used at the equivalence point, 29.16 repeating. Again, I'm going to use all the numbers so that we get a true half equivalence point. All right, and so I want to know what is my molarity now that our volume is, we have to add 35 to that, 64.16 repeating. And then for your NH3, we had 0.20 molar. We had 35 mils. Now, what is the molarity now that we're at 64.16 repeating? So 29.16 times 0.12 divided by 64.16 repeating, and that gives us 0.054 repeating. So that just keeps repeating 5454. I'm going to leave that in there. For the NH3, I got 0.2 times 35 divided by 64.16 repeating. And that is a 1.09, the 09 repeating. 0.109, it keeps repeating the 09. All right, and so my H plus, 0.054 repeating, and this is your 0.109, the 09 repeating. This one is not as obvious to see, but that is exactly half. The half equivalence point will always be you added exactly half of your H plus or your OH minus of that of your NH3. All right, and so the 0.054 is a smaller number, 0.054, and the 54 is repeating. So when I subtract 0.05454, I just keep pushing 54, and I push enter. I get, since it's exactly half, I get 0.054 repeating. This is 0, and then this is the plus 0.054 repeating. 0.054. So at any time that you do a half equivalence point, an easier number would have been to pick a 2 here, and then the half equivalence point is a 1 here. This one's going to be 1, this one's going to go 0, this is going to be 1. Every half equivalence point, your NH4, your weak acid, and your weak base will have exactly the same concentration. All right, and you have the weak acid along with its conjugate weak base. You have a buffer. And so your pH is equal to the pKa plus the log of your A minus over HA. And so your pKa, you take your 5.6 times 10 to the minus 10. So your Ka is 5.6 5.6 times 10 to the minus 10. So the pKa is the negative log of that. So when you take the negative log of that, you get 9.25. So your pKa, 9.25. So your pH is equal to 9.25 plus the log of A minus 0.054 repeating, 0.054 repeating for your HA. So the half equivalence point, these are always the same. And so it's always the log of 1. And so your pH is equal to the 9.25 because the log of 1 is 0. So when the question is, what is the pKa at the half equivalence point? What is pKa? What is the pH at the half equivalence point? It will equal your pKa. So there's really no calculation to do unless you need to calculate the Ka and the pKa. But we had already done that in a previous problem where we had a buffer and we already had our pKa. And so we already had our answer. So once you have calculated the pKa, you know the pH at the half equivalence point. Because at the half equivalence point, your A minus and your HA are exactly the same concentration. The log of 1 is 0. And your pH is equal to your pKa. All right, so do not miss the easiest question on the test, which is simply the pH at the half equivalence point. That is the pKa. All right, then we added 70 mils of HCl. So the equivalence point was 58.3 repeating. So we went past the equivalence point. So now we have 70 mils of 0.12 molar HCl added to our 0.20 molar and 35 mils of our NH3. All right, so again, we have MV is equal to MV. For the H plus, we have MV is equal to MV. For the NH3, we had 0.12 molar at a volume of 70. What is the molarity now that our volume is 105? Over here, we have 0.20 molar when the volume was 35 mils. What is the molarity now that we are at 105? So we need our new concentrations. 0.12 times 70 divided by 105, 0.08. And 0.2 times 35 divided by 105 is 0.06 repeating. That just keeps repeating the 6. All right, and so again, we have the same exact reaction. NH4 plus in equilibrium with H plus and NH3. And we plug in our initial. 0 for the NH4, H plus is 0.08. The NH3 is 0.06 repeating. Now we see that the 0.06 repeating is the smaller number. And so our NH3 is going to 0, our H plus is 0.013 repeating. And then, of course, our NH3 now is 0.06 repeating. All right, but the question is, what is the pH? Now, what you have to remember, this is our new initial. All right, so you can go through all of the calculations. All right, so change equilibrium, minus X plus X plus X, 0.06 repeating minus X, 0.013 repeating plus X, and X. All right, when you have an initial concentration of a reactant and an initial concentration of a product, the X's can be neglected and they do not need to be checked. All right, so that means the minus x will have zero effect, the plus x will have zero effect. Anytime you have an initial concentration of a reactant and a product, your initial concentration and the equilibrium concentration will always be exactly the same. So anytime you have a starting concentration of a reactant and a starting concentration of a product, then your initials, which would be in this case new initials, will be exactly the same as your equilibrium. You always have to have a zero on the right. Anytime you write Ka, Kb, Kw, something or both things have to be zero on the right. So when we started, neither one was zero. And so you're going to react until one of those is zero, the one you have the least amount of. All right, and so there you have your answer. Your answer is this is not a buffer because a buffer has to have zero H plus. This is not zero H plus, it's 0.013. But since we also have an NH4, we know this number is not going to change. And so you don't have to do anything. You just go right to the pH. pH is equal to the negative log of 0.013 repeating. So the negative log of 0.013 repeating is 1.88. So your pH here is 1.88. All right, if you went through and you calculated x and you added 0.013 repeating to x, you would get zero change in that number. Again, you don't do the, did we not do that up here? Yeah, we did. You don't do a Ca over Ka when you have a reactant and a product. When you have an initial concentration of a reactant and a product, you never have to check your x value. X1 is your final answer. All right, then we're going to draw a graph. All right, so when you draw your graph, only one thing is always the same, and that is you have pH on the y-axis. All right, sometimes you're adding strong base, sometimes you're adding strong acid. This time we were adding strong acid, so it is the volume of HCl, which means that we started with a base, a high pH, and then as we added our HCl, the pH became lower and lower. Again, you're not going to draw this to scale, but you'll have to label it. So when you have that sharp, straight down motion, that is your in pH, that is your equivalence point. So this is your equivalence point. All right, which means this is the 58 mils. We'll just go with 2 sig figs. And our 5.19, I think we got for the pH of that. At the equivalence point, whatever we got for the pH at the equivalence point, you just label it. Then you would go to your 29 mils. So right halfway between the 0, here is 0, and the 58, that is your 29 mils, and that is your half equivalence point. All right, and so you go up here and you say, here's my 9.25. All right, so your pH is equal to your pKa at the half equivalence point. All right, you also had other points. You had your 20 mil point that we did the other day, and that was, well, something above 9.25. If we scroll up, we can probably find that answer. 9.54, so it should be right there next to it. 9.54. So that is your pH there. And then when we added nothing, no HCl to it, that was 11 point something. So we go back up in our initial concentration before adding anything, any H plus, 11.28. So when there was 0 base, 11.28 was our pH. The one we just did said we added 70 mils, so we'll mark this one at 70 mils. And then we go up, and this is your 1.88. Right? So you're not going to be given graph paper and draw it to scale, but you just label the points that you were required to come up with on your problem. And that is how you do your graph. Of course, if we're adding volume of base, then you're going to go here, pH always here, so you're adding base, so the pH is going to go up. And the inflection point, the point where it goes up the highest, this is your equivalence point. All right, and so this is your pH at the equivalence point. The only thing you can say about that on a non-labeled scale is it's greater than 7. But if it says calculate the pKa of this acid, so this is a weak acid with a strong base, then you are looking at, if this is your equivalence point and this is the 0 point, you don't even need to know the numbers. You just have to go halfway through it. So this is the half equivalence point. And so that number right there is your pKa, because the pH is equal to the pKa at the half equivalence point. So you can get your Ka or your pKa from a graph. You just have the graph. You can find out where the big inflection point is, find your equivalence point, go halfway from the beginning to the equivalence point, draw a line up. That pKa, that pH is your pKa for that acid. So you can find your pKa from a graph. All right, so that will definitely be the hardest question on the test because it's every question in the book in one problem. All right, so let's do some of the homework problems. Let's see. We'll start with 16.36. All right, on 16.36, we've got 0.2 molar of an acid. So it names the acid, it doesn't matter. We have 0.20 molar of an acid. And it has a pH of 3.12. No, 3.21, sorry. 3.21. Calculate Ka. All right, so you'll be given an initial concentration and pH. You'll have to find Ka. You'll give an initial concentration Ka. You'll have to find pH. You'll be given a pH and a Ka, and you'll have to find the initial concentration. 2 out of these 3 have to be given. All right, and so you have HA and only HA. So that's the only reaction that you write. HA goes to H plus and A minus. And the Ka, well, that is what we're looking for. Note when you have pH, pH is equal to the negative log of your H plus concentration. You need to know that this H plus concentration is at equilibrium. When we take the pH, we always take the H plus concentration at equilibrium. In the last example, the H plus initial and equilibrium were the same. All right, well, that could be true. But in this case, since we started with 0, the final is never 0. All right, and so we have initial 0.20, 0, and 0. There's no new initial. If you have any one of these on the right is a 0, you don't have a new initial. The only time you have a new initial is if both of these are not 0. All right, and so it has to go to the right, 0.20 minus x, x, and x. And so at equilibrium, you have, oh, that's just minus x. That's what you have. You have minus x here, you have plus x, you have plus x. All right, so at equilibrium, you have 0.2 minus x, and you have x, and you have x. So the usual Ka is equal to x squared divided by 0.20 minus x. All right, and we can't have 2 unknowns. We can only have 1 unknown, and that 1 unknown is the Ka. So therefore, we must have enough information to find x. Well, since the H plus concentration is x, and they give us a pH, we then find our concentration of H plus at equilibrium. So you have your 3.21 is equal to the negative log of your H plus concentration. So you take the negative of both sides. So now we have negative 3.12. Then you push your anti-log button on your calculator. That is your 10 to the x button. And you get that your H plus concentration, which we see right here, is equal to X when we did our initial change equilibrium, and that is 10 to the negative 3.21. And so you get your calculator and you have your 10 to the negative 3.21, and that is 6.2 times 10 to the minus 4. So that is equal to your H plus concentration, which more importantly is equal to X. And now we just plug it in. Everywhere you see an X, you put 6.2 times 10 to the minus 4. So Ka is 6.2 times 10 to the minus 4 squared divided by 0.20 minus 6.2 times 10 to the minus 4. And then you just push the buttons on your calculator. All right, you get 1.9 times 10 to the minus 6. And what I was trying to do is figure out same answer probably. So. Yeah. All right, so if you don't stick in the number in the minus x here, in this case, you will get the same answer. Many times you will not. Always, if you have your x value, always plug it in. If you want to do a calculation off to the side and say my initial concentration is 0.2, here's what I got for my Ka, so I don't have to change it because 0.2 divided by 1.9 times 10 to the minus 6 is greater than 1,000. All right, so if you get a number and then you check it like that, well, then that's fine. But if I have my x value, I put it in everywhere where there's an x because many times it will matter. Sometimes, like this one, it does not. You got a 50-50 chance. So I would put it in and get it right 100% of the time. Even though we didn't need to this time, fine. We still got the correct answer. If we did need to do it and you didn't put it, then you have the wrong answer. All right. That was 36. Let's do 1638. All right, so we have formic acid. Again, as soon as I see formic acid, I write HA. Feel free to write the whole thing if you want. I write HA. All right, what is the pH of a 0.12 molar solution? All right, and so I want the pH and the degree of ionization. And the Ka, you look it up on table 16.1, 1.7 times 10 to the minus 4. All right, so we added 0 H plus. There was nothing about HCl in this problem. There was no A minus. And so they're both 0. So you're ready to go to change in equilibrium. All right, so minus x plus x plus x. You cannot have a 0. 0.12 minus x, x and x. So x squared over 0.12 minus x is equal to, this is the Ka reaction. This is the Ka constant. You should always make sure that you have the correct constant for the equation that you are writing. Now, this one is going to be very close, so you must check it. It has to be greater than 1,000, or you have to either do the quadratic or check your x value. So when you take your 0.12 and divide by the 1.7 times 10 to the minus 4, So 0.12 divided by 1.7 times 10 to the minus 4, you get 705, which means you cannot use x1. 705 is not greater than 1,000. All right, and so now you have your choice. You can do quadratic equation or you can do successive approximations. I will almost always pick successive approximations. So you neglect that. You take your 0.12 times 1.7 times 10 to the negative 4. Take the square root of that. Your x1 value is 0.0045. And this is close to 1,000. So this is going to take maybe 3. Maybe it's x1 is the answer. We're going to find out. That's as high as it can be. All right, so now we plug that in. All right, so we're going to plug it in. So 0.12 minus that answer times 1.7 times 10 to the minus 4 and the square root of that, and you get 0.0044. So it does change it slightly. All right, and so either we're going to get 0.0044, which is a 90+% chance, but it's possible that it goes back up to 0.0045. So you take your 0.12 minus that answer times 1.7 times 10 to the minus 4 and the square root of that, and you get 0.0044. All right, so that is X. All right, and so X is the H plus concentration. If this is a multiple choice, you get 705. If I do these calculations and use 0.0045 versus 0.0044, there's not going to be a multiple choice answer that's going to be that close together. All right, and so your pH is equal to the negative log of your H plus. You have to make sure that your X is your H plus. You then confirm that your X is your H plus, and so this is 0.0044. So the negative log of 0.0044. And that is a 2.36. All right, it also asks for the degree of ionization. Okay, it didn't ask for percent, so don't multiply it by 100. Just take X over initial. If they wanted percent, then you multiply by 100. So 0.0044 divided by the initial concentration of 0.12. So 0.0044 divided by 0.12, and that is a 0.037. Or, again, 3.7%. But they asked for degree, so 0.037. If they asked for percent, you multiply it by 100, it would be 3.7%. All right, that was 1638. 1640. All right, we have an acid with a lot of letters, and I say HA is prepared. Okay, calculate the concentration of hydronium ion. Okay, again, you know that the OH is called hydroxide. The H plus is called the hydrogen ion, but H plus is the same as H3O plus. So the hydronium ion is the H3O plus. You know everything else, and so you can get what the hydronium ion is by process of elimination. And they also want the A minus. They want the 8 ion, which means it's a negative ion. And we have a 0.1 molar acid. And the Ka is 9.8 times 10 to the minus 5. So we can check our CA over our KA and see if that is greater than 1,000. So you take your 0.1 divided by your 9.8 times 10 to the negative 5, and you get 1,020. Okay, so barely, but yes. So 1,020 is slightly greater than 1,000. So we are good. So X1 we can use as our final answer. All right, and so you go minus x, and then equilibrium, 0.10 minus x, and x. So x squared over 0.10 minus x is equal to 9.8 times 10 to the minus 5. Again, make sure you got the Ka reaction and you're using the Ka constant, and that is what we are doing. All right, so since it was barely over 1,000, but over 1,000, we can neglect our x. We do not have to plug it in. You can if you want. It should not change, and if it does, it's going to change at such a small amount, it will not affect the answer. All right, so 9.8 times 10 to the negative 5 times 0.1, and then we want the square root of that, 0.0031. All right, so that's your x value. Then you have to know what x is. X, again, here is H+. We're in the acid part of the problems. They're not labeled for you on the test, so you have to check to make sure that H is your H+. In this case, it is. And 0.0031, this is 0.0031, so both of these concentrations. And when you take 0.1 minus that answer and you give it to, I will accept two answers here. I will accept that it has changed as a 0.10 molar, or after you do the subtraction, if you give it 2 sig figs, I would also accept that as a 0.097. All right, so sig figs I'm not going to be counting, but 2 sig figs is what you should be giving for our concentration. So if you say that technically by sig fig rules it is 0.10, but if you give it as 0.097, again, both of those are 2 decimal places, and both of those would be counted as full credit answers. All right, and so the question was calculate the pH. So pH is equal to your negative log of your 0.0031. So the negative log of 0.0031 is a 2.51. All right, 40 is that all that's for? And then it said, what is the concentration of A minus? That is 0.0031. That was all the questions for that one. 1642. 1642, chemists want to determine the concentration of a solution of lactic acid. All right, so again, that to me is AJ. From the pH of the solution was 2.6. So pH 2.6. What was the concentration of the solution? The Ka is 1.4 times 10 to the minus 4. All right, so as I said when we did the other one, you have to be given an initial concentration and a pH, an initial concentration and a Ka, or a pH and the Ka. You have to have 2 of the 3. In this case, this is the first one that we've had where the initial concentration is unknown. All right, so we have our HA that goes to H plus and A minus, and we know the Ka is 1.4 times 10 to the minus 4. And so initial, we have some initial concentration. I will call it Y. Call it any letter you want. All right, and then we didn't add any H plus. We didn't add any of the A minus. The reaction has to go to the right. So minus X plus X plus X. So at equilibrium, we have y minus x, we have x, and we have x. All right, and so we have x squared over y minus x is equal to the Ka. All right, so this is the Ka reaction. That's the Ka constant. Now, what we do have is Ka, so we can plug in a number for Ka. We know that that is 1.4 times 10 to the minus 4. The other thing we know is the pH is 2.60. So from that, we know that the pH is equal to the negative log of the H plus concentration, and that is at equilibrium, which is our X value. And so once we know our Ka, which we do, and then we plug in our X, we only have one thing to solve for, which is all that we can solve for. All right, and so your H plus concentration, which is equal to X, we take the negative of both sides, so that gives us a negative 2.60, and then we push our inverse log button, and that is our 10 to the X button. So that is 10 to the negative 2.60. Make sure you can do this on your calculator. All right, and so your H plus concentration is 0.0025. So that is your H plus, that is your X, and now we just plug that in and solve for Y. So we have 0.0025 squared. We have Y minus 0.0025. That is equal to 1.4 times 10 to the minus 4. So everywhere where we had an X, here is our X value. That is the H plus, that is the X. We plug it in there, we plug it in there. We have our Ka, we just have Y to solve for. But this again is an algebra equation that we have to solve. So to solve this, we have to multiply both sides by Y minus 0.0025. And when we multiply this side by Y minus 0.0025, that is canceled. All right, 0.0025 squared, that is 6.25 times 10 to the minus 6. And then we distribute our 1.4 times 10 to the minus 4. So that is 1.4 times 10 to the minus 4 y minus 1.4 times 10 to the minus 4 times 0.0025, which is 3.5 times 10 to the minus 7. All right, so then we have to add 3.5 times 10 to the minus 7 to both sides. We have to add 3.5 times 10 to the minus 7 to both sides. And so here we will have 6.6 times 10 to the minus 6 when you add that on your calculator. And that is equal to 1.4 times 10 to the minus 4. All right, so then we divide both sides by the 1.4 times 10 to the minus 4. We divide both sides by 1.4 times 10 to the minus 4. And we get 0.047. And so our initial concentration of our acid is 0.047. All right, and so if we were to check to see if we could have neglected our X here, all right, so like I said, sometimes you can neglect your X. All right, so we had no way to know if we could neglect this or not. So if you don't know, you never neglect it. And we can test later to see if we wasted our time or if that was required. And so our initial concentration of A over Ka, so our 0.047 that we calculated, the 1.4 times 10 to the minus 4 that they gave us for Ka, and that gives us 336. So no, if you would not have put it into the y minus x, you would have gotten a slightly different answer, which again, if it's multiple choice, you're probably close enough to get the right answer, but if it's work out the problem, you did not do it correctly. All right, so that one is 42. All right, 16.46. All right, what is again, hydronium? You have to get used to the words. Hydronium simply is H3O plus, but again, I always use H plus. They are the same. All right, so, oh, this one is interesting. All right, what is the hydronium in a very small concentration of an acid? Again, I'm not going to write up the p-bromobenzoic acid. I'm writing HA, all right, because that is what that is. All right, and the Ka for that is 1 times 10 to the minus 4. So HA goes to H plus and A minus. All right, so initial, we had 3 times 10 to the minus 4. 0 and 0. So when you take your Ca over your Ka, you have 3 times 10 to the minus 4 over 1 times 10 to the minus 4. I don't need a calculator for that. That is 3 and nowhere near 1,000. All right, so if you're going to do successive approximations, it is going to take a lot of them. All right, so when my calculation of Ca over Ka is less than 100, I know that is probably going to be better off doing a quadratic equation rather than successive approximations. But either one will work. So 3.00 times 10 to the minus 4 minus x plus x and plus x. So that's your change. That's your equilibrium. At equilibrium, minus x, x, and x. So you have x squared divided by 3.00 times 10 to the minus 4, ridiculously small initial concentration, minus x is equal to 1.00 times 10 to the minus 4. All right, well, let's see. I'm going to do x1 and x2 and show you that this is probably not the way to do it. All right, so we definitely have to check it. So you have 1 times 10 to the minus 4 times 3 times 10 to the minus 4. And then you take the square root of that. And that is 1 point. And then unfortunately, they keep giving 3 sig figs in this one. 1.73 times 10 to the minus 4. All right, so then you plug that in there to get x2. 3 times 10 to the minus 4 minus that answer times 1 times 10 to the negative 4 and the square root of that. And you get 1.13 times 10 to the minus 4. So we're between 73 and 13. Plug that in. 3 times 10 to the negative 4 minus the previous answer. And you get 1.37 times 10 to the minus 4. Plug that in. .28. Plug that in. .31. All right, only one or two more here. Okay, so 3, 4. Oh, 1.30 times 10 to the minus 4. So I know my next answer is my final answer. So 3 times 10 to the negative 4 minus that times 1.30 is the answer. So it took 7 approximations. So 1.30 times 10 to the minus 4. If there were only 2 sig figs, it would have taken just the 5 approximations. But since they gave 3 sig figs, I went out with 3 sig figs. All right, and so my X is the H plus concentration, and so your pH is equal to the negative log of 1.30 times 10 to the minus 4. All right, it asks for the hydronium ion concentration, which is that. So it's 1.30 times 10 to the minus 4 molar. That is the answer to the question. I always then calculate the pH. It didn't ask for it, but I will calculate it. So the negative log of that is a 3.88. So the pH is 3.88. All right. So again, there, when you have your initial concentration divided by your Ka, if you got a number less than 100, well, less than 10 in this case, you're going to have at least 5 or 6 approximations before it's the same. So you'll have to make that decision whether you want to do the quadratic or keep plugging in your X value. All right, 1648. All right, so this is a diprotic acid. So you got carbonic acid. CO3 is pretty easy to write. You can write that if you wanted to, but I'm going to be consistent and always use A. All right, so you have a Ka1 for carbonic acid of 4.3 times 10 to the minus 7. You have a Ka2 of 4.8 times 10 to the minus 11. So you can look those up on the chart. Ka2 is always smaller than Ka1. If you had a Ka3, it would even be smaller than the Ka2. All right, so calculate, okay, good. I was like, calculate the hydronium ion concentration. All right, so we want the H3O plus concentration again. All right, because if it says, what is the, because it does say, and what is the concentration of CO3 minus 2? So I already know the concentration of CO3 minus 2. That is 4.8 times 10 to the minus 11 molar. So there's no calculation required to get the A minus 2 ion. You do it once, you never have to do it again. We will do it again. But it will be 4.8 times 10 to the minus 11. Just like the pH is equal to the pKa at the half equivalence point, the concentration of your minus 2 ion is always equal to your Ka2. All right, so we have our H2A. We do the Ka1 first, H plus, and HA. A minus. That is your Ka1. 1 H comes off at a time. 4.3 times 10 to the minus 7. My initial concentration was 6 times 10 to the minus 4. We like very small initial concentrations now. All right, 0 and 0. Now we have to calculate, do we have to check our X value, or is X1 our answer? So you have to do CA over the KA1. So 6 times 10 to the minus 4 divided by 4.3 times 10 to the minus 7. And we lucked out. We got 1,395, so we got about 1,400. And so X1 is the answer. All right, so we do not have to check our values. So minus X plus X plus X. So 6.00 times 10 to the minus 4 minus X. X and X. And so you have your X squared over 6 times 10 to the minus 4 minus X. Is equal to the 4.3 times 10 to the minus 7. We can neglect this X, and since our CA over KA was greater than 1,000, we do not have to check it. So we have 6 times 10 to the minus 4 times 4.3 times 10 to the minus 7. And then we take the square root of that, and that is our answer for X. And so we have our X value, and that is 1.6. Well, it would be at 1 there. Let's just go, that's 2 sig figs. 1.6 times 10 to the minus 5. All right. So our H2A concentration is not going to change. It is here. If you subtract it and you get something else, that's fine, but that's basically not going to change. But it actually would change in that number of sig figs given. If you're giving it to the right number of sig figs, yeah, it is going to change. So you would take 6 times 10 to the minus 4, and you're going to actually get a 5.84 times 10 to the minus 4 molar, which is odd since your CA over your KA was greater than 1,000. That pretty much means it's not supposed to change. All right, but that again is a rule of thumb, and that's what we're going with. If that is greater than 1,000, you don't have to check it. In this case, if we would have checked it, we would have got a different answer, at least at 3 sig figs. All right, and so we have 1.6 times 10 to the minus 5 molar for our H plus, 1.6 times 10 to the minus 5 molar for the HA minus. All right, so then we do our KA2. All right, so for KA2, we have HA minus goes to H plus and A minus 2. This is our KA2. The second H comes off, and that was given as 4.8 times 10 to the minus 11. Now, initial is from KA1. HA minus is our X value. That is 1.6 times 10 to the minus 5. The H plus, also X, 1.6 times 10 to the minus 5. And the A minus 2 is 0. All right, and again, we're doing this to find A minus 2, except we already know the answer. All right, so change. Minus X plus X plus X, equilibrium. 1.6 times 10 to the minus 5 minus X, 1.6 times 10 to the minus 5 plus X, and X. Again, when you have an initial concentration of a reactant and you have an initial concentration of a product, the concentration never changes. So whatever your initial concentration is, the equilibrium concentration will be exactly the same, which means you can neglect your X's. You do not have to check them. All right, so when you take your 1.6 times 10 to the minus 5 plus X times X divided by your 1.6 times 10 to the minus 5 minus X, and that's equal to 4.8 times 10 to the minus 11. We can neglect our plus and minus X. We do not have to check it. And then we see we have the exact same number. 1.6 times 10 to the minus 5 cancels 1.6 times 10 to the minus 5. And we get X is equal to 4.8 times 10 to the minus 11, which we answered before we started the problem. The A minus 2 concentration is 4.8 times 10 to the minus 11 molar. It is always the same as Ka2. And your pH, if you add this extremely small number, 4.8 times 10 to the minus 11, it does not change to 1.6 times 10 to the minus 5. Anytime you have a diprotic acid, all of your H plus is going to be from Ka1, because when you have an initial here, you're also going to have an initial here. And when you have an initial reactant, initial concentration of a product, at equilibrium, it never changes. And so there is your H plus concentration. All right, so you only have to do Ka1 if the question is just calculate the pH. And so your pH is equal to the negative log of the 1.6 times 10 to the minus 5. Actually, I think it asks just for the H3O plus concentration, which is equal to your H plus concentration, which is your first X value, 1.6 times 10 to the minus 5 molar. But if we want the pH, negative log of 1.6 times 10 to the negative 5, we have a pH of 4.80. All right, so I'm given the pH. They're not asking for the pH. They're asking for the concentration of H3O plus, which you need in order to find the pH. All right, last one is going to be 52. Finally, we get to a base problem. 1652. And these are not going to be organized on the test, as this one is base and this one is acid. All right, so you have trimethylamine. Again, you can write out the whole formula. I have a base. I write A minus plus H2O goes to HA and OH minus. I know them all. You only need to know three reactions: the Ka, which is what we used every time so far. Now, finally, the Kb and Kw. And something on the right has to be 0 before you can go to equilibrium. So if you have an initial where two things on the right are not 0, you need a new initial. Something on the right has to be 0. All right, so we have 0.25 molar of the weak base. And it has a pH of 11.63. What is the Kb? All right, so again, initial concentration, pH, Ka or Kb. Those are what we're going to solve for. So this is done exactly the same way we did our first problem, where we solved for our Ka. Except these are 0 and 0, and so has to go to the right. Minus X, again, water. Don't worry about water. Plus X. Water is a liquid, not in your equilibrium. So 0.25 minus X, X, and X. So we have X squared over 0.25 minus X is equal to the Kb. This is the Kb reaction, and so now it's equal to Kb. All right, so the question is, what is KB? Well, we now know we have to find X. And X, we see, is not H plus anymore. X and a KB is OH minus. So if your pH is equal to 11.63, then you know that your pOH is equal to 2.37. Because when you add those up, you always get 14. All right, and so you also know that the pOH is equal to the negative log of your OH minus concentration. And so you have your pOH now, 2.37. That's equal to the negative log of OH minus. You got to take the negative of both sides and then your inverse log button, which is your 10 to the X button. And so your OH minus concentration, which is equal to your X value, is equal to 10 to the negative 2.37. And that gives you a 0.0043. So that is your OH minus concentration, which you see over here is your X value. And so you simply plug that in for X and you get your KB constant. So we have 0.0043 squared over 0.25 minus 0.0043. And that is equal to the KB. So you just plug in your numbers. And that gives you a 7.5 times 10 to the minus 5. All right, the other part of this problem says you have 0.35 molar of this same trimethylamine, and what is the pH? All right, so again, now we have the Kv, that's a constant, and we have the initial concentration. We can find the pH. And since the initial concentration of the first problem was a 0.25 molar, what we can say is that it's going to be higher than the previous pH, so it's going to be greater than 11.63. And so you simply have your X squared over your 0.35 minus X is equal to 7.5 times 10 to the minus 5. And your CB over your KB is greater than 1,000. And so that is your final answer. And so again, here X, you have to know X is your OH minus concentration, and that is 0.0051. And then the negative log of that is a 2.29, but that is a pOH. And so subtract that from 14, and you get your 11.71. All right, so it is greater than the initial one, which was a 11.63. Barely higher, but higher. All right, we will pick up there next time. Test is on Thursday.